Okay, welcome to the third in our series of XACC Tech Talks. My name is Cathal McCabe from the Xilinx University program. I'm going to start as usual by briefly introducing the XACC program, and we'll move on to our two speakers for today. The Xilinx Adaptive Compute Clusters program is a special initiative from Xilinx to support novel research in adaptive compute acceleration. The scope of the research covered by this program is broad, from systems to architectures, tools, and applications. The program is managed by XUP, and over the last year, we set up 4 XACC host centers at the universities shown. These are intended as community resources for researchers around the world to use remotely. The centers consist of servers enabled with Xilinx Alveo compute acceleration hardware, and we invite interested researchers to join the XACC community. For more information and to apply, you can see the XACC webpage where you registered for this talk. This series of talks is on research related to the program. If you missed any of the previous sessions, you can also find recordings on the XACC webpage, and a recording of this talk will be posted in the next few days. Our first speaker today is Dr. Haris Javaid, a colleague from Xilinx Research Labs in the Xilinx CTO department. He will present on blockchain machine accelerating validation bottlenecks in Hyperledger Fabrics.
Okay, thanks, Cathal. Thanks for the introduction, and welcome everyone, and thanks for coming to my talk. Today I will present some of our work on blockchain machine, which is a hardware accelerator for permission blockchains. So I will give a little bit of background on permission blockchains and Hyperledger Fabric specifically, and why we are interested in permission blockchains. Then I will introduce our hardware accelerator blockchain machine and how we designed it based on some of the performance bottlenecks we identified in Hyperledger Fabric. I will conclude my talk with some of the results and how we are going to make this open source and available to the community. Before I go into the technical details, I would like to thank my colleagues who have contributed significantly to this work. So let us start with a real-world use case of a blockchain application. IBM recently created a blockchain-based system called Food Trust, where the idea was to connect retailers or suppliers with consumers like us. So as a consumer, I can go to a grocery store like Walmart and scan a barcode and try to see the fruit which I picked up, let's say mangoes, where they were actually planted and grown, and when they were picked up, and how long they have been on the shelf in Walmart. So this is a very useful application and a real world use case for a blockchain system. But the real challenge comes when we want to take these kind of test systems and scale them up. For example, if you would like to include all suppliers and all products in Walmart, then one could see that the estimated transactions per second that such a blockchain system should be able to process would be in 100,000s or even millions of transactions per second. And then when we look at the current software-only implementations for blockchain systems, what we find out that they are really far behind the performance or throughput requirements of these applications if we really want to scale them up in the future. So what at Xilinx we believe is that some of these scalability issues of blockchain systems can really be solved using hardware acceleration, and can actually pave the way for widespread adoption of blockchain systems. So irrespective of the type of blockchain system, they all have some form of scalability issue. So let me now come to the different types of blockchain systems which are available nowadays. Many of you would already know about Bitcoin and Ethereum. These blockchain systems are categorized as public blockchains because anyone can take part in the blockchain network. For example, I can buy a machine right now and basically connect to the Bitcoin network or the Ethereum network. And because of that, these public blockchains generally use a consensus mechanism like proof of work, which is very power hungry and computationally very intensive. The other type of blockchain systems which are emerging nowadays are called permission blockchains. The idea there is that the nodes which can take part in the network are restricted. So as an example, we can set up a permission blockchain system between two organizations. And then only the nodes which are part of those two organizations can take part in that network. So because of this, the permission blockchain systems are gaining a lot of popularity in enterprises because they can actually implement distributed enterprise applications on top of permission blockchains. So when we look at a lot of different permission blockchain systems available nowadays, Hyperledger Fabric is one of the most popular ones. And there are many companies which have actually used Hyperledger Fabric already to deploy and develop hundreds of applications on top of it. And it's an open source project, so anybody can actually take it and use it. In fact, the IBM Food Trust example I just gave in the last slide is also based on Hyperledger Fabric. So let me go into a little bit of more details of how transactions in a Fabric network flow. So there are a number of nodes in the network, for example, here at the top. So there's a client, some peers, and then some ordering service. Generally, a client is responsible for creation of a transaction, which is then sent to peers in Hyperledger Fabric called endorsing peers. What this means is that the endorsing peers will execute the transaction and ensure that it's actually executable and get the results of the execution of that transaction, and then sends back that results to the client with an endorsement. The endorsement here means that the peer will actually digitally sign or cryptographically sign the results of that execution of the transaction. The key point to note here is that these transactions are not yet committed into the distributed ledger or the blockchain itself. When the client gets enough endorsements from different peers, then it will send that transaction to another type of node called the ordering service or orderer. The orderers are responsible for gathering all the transactions and creating an order between those transactions and then create blocks out of those transactions. Once a block is created, then that block is sent to all the peers in the network, for example, here and here. These peers would then validate the block, all of the transactions in the block, and they run various types of different validation checks. And if the transactions are valid, then they are actually added to the distributed ledger. And once a transaction is committed to the ledger, then a notification is sent back to the client notifying that the transaction has actually been committed. So if you look at this Hyperledger Fabric flow, the consensus mechanism generally is executed in this orderer part here. And then the cryptographic authentication and validation of transactions and their data happens here in the validation phase. And the endorsement phase is generally for execution or simulation of transactions. So keeping that in mind, I would like to go into a little bit of more details of the validation part in Hyperledger Fabric. So here is the typical data flow of how a block goes through different validation operations during the validation phase in a validator peer of Hyperledger Fabric. The first thing the peer does is it will verify the block. So by verifying a block, what it does is that it will look at the digital signature or the cryptographic signature of the orderer on the block and verify that signature is correct. Then it will look at the signatures on each of the transactions and ensure that those signatures can actually be validated. And then it will run something which is called validation system chain code or VSCC, where it will validate and verify all the endorsements which were initially produced by the endorsing peers on this transaction. So you can see that this validation and verification here involves a lot of verification of cryptographic signatures. And by default, Fabric uses elliptic curve cryptography-based ECDSA scheme. So basically, this means it would be verifying a lot of ECDSA signatures here. The second step here involves accesses from the database. So each peer locally keeps database called state database, which is basically a snapshot of the entire blockchain or the distributed ledger at a particular time. Let's say I have two transactions in the block where first transaction transfers $10 from an account to a second account. And then there's another transaction which transfers another $30 to the second account. So the database would only have the final value of that account. So that's the state database. In this step, the peer will read from the state database and ensure that the reads which were done during the endorsing phase by the endorsing peers are still the same, which ensures that there have no changes to the database in the meantime. And if these checks also pass, which are called the MVCC or multi-version concurrency control checks, then the transaction is marked as valid. And then in the last step, the number third here, the block is actually added to the blockchain or the ledger. And then all the transactions which have been marked as valid, their updates are applied to the state database. So when we look at this validation phase and look at some of the very recent works published on benchmarking of Hyperledger Fabric, all of these works highlight that this validation phase is the major bottleneck for Hyperledger Fabric. And this is also kind of applied, could be applied to other permission blockchains because the consensus mechanism is only run within a few nodes and is not the bottleneck. Instead, the cryptographic verification and authentication of nodes and transactions becomes the bottleneck. Unlike public blockchain systems like Bitcoin or public Ethereum, where the consensus mechanism based on proof of work becomes the bottleneck instead of the validation or verification. So we also conducted a study ourselves. And instead of going into all the details here, what I would just like to highlight is that we were able to draw four major observations from our own in-depth analysis and study of the validator peer in Hyperledger Fabric. So this graph here on the left-hand side basically reports the percentage time spent during the profiling in different operations of the validator peer. And the graph on the right-hand side here shows the total time spent in the coarse-grained operations of the validation phase. So what we can see from here is that the ECDSA signatures during the verification and the validation basically take about 40 to 50% of the time in a validator peer. And then afterwards, either it's accessing the block data or the transaction data from the block itself, or accessing the state database, which becomes the bottleneck. And there's also some writing into the ledger, if you recall from the previous slide, that finally the block is actually written into the ledger. So this operation is more IO-bound operation instead of a CPU-bound operation, and hence is not is not a CPU compute-intensive task. So from this, what we realized that all of these compute-intensive operations can actually be accelerated using hardware, while the non-compute-intensive task could actually be kept on the CPU side. So we can carefully design an accelerator which can speed up only the bottleneck operations in hardware while still keeping non-bottleneck operations in software. So with that goal in mind, we came up with this accelerator called Blockchain Machine. And the goals, as I have mentioned earlier, were to design FPGA-based, were to design hardware accelerators, although we chose FPGAs as the platform for implementation. The reason for choosing FPGAs is that the permission blockchain platforms are just a platform for implementation of more applications on top of it. And applications can have different workloads. And if we want to customize the accelerator, the FPGAs provide us the flexibility to actually customize and make it more optimized for particular applications that are actually developed and deployed on top of a permission blockchain. And we need to look into both the hardware and software sides of this validation operations to only offload those operations which are really compute intensive and can actually benefit from acceleration. So our current proposal implements this validator peer on a network attached Xilinx LVO card. And to achieve that accelerator, we first propose a hardware-friendly protocol to send blocks from the orderer. The idea, high level, is to ensure that we can retrieve the block data and the transaction data right in the hardware without any involvement of the CPU. And then we propose another efficient and configurable pipelined compute accelerator to actually accelerate the validation operations in hardware. And as of now, we have actually implemented this accelerator and integrated it with Fabric v1.4, which is available online and is open source and can be used by anyone. So here is the overall system setup of the blockchain machine. So as you can see, we have a standard server with multi-core CPUs, and then an FPGA card plugged into the PCIe slot. Inside the FPGA card, there is an integrated network interface, which can give us the connectivity to the network. And then from here, these three boxes, these three modules basically represent the architecture of the hardware accelerator. The protocol processor, the first module here, is responsible for looking at all the packets that are coming through this FPGA card and only parsing and processing those packets which are intended for the blockchain machine. In other words, it only processes those packets which are sent through our own hardware-friendly protocol. All the other packets which are not intended for the blockchain machine are just passed through to the CPU. The main idea, the key takeaway here is that this acts as a streaming kind of an architecture where block data just streams in through the network interface. Without the involvement of the CPU, it's retrieved and accessed within the FPGA, and then it's forwarded to the block processor for further execution of the validation operations. The block processor module at a high level is integrated block level and transaction level pipeline, so it can actually process multiple blocks and transactions at the same time. And the reason for using a parallel pipeline architecture internally is to ensure that we can achieve very high throughput. And internal components of the block processor generally include many ECDSA verification engines, key value-based database, and different sorts of control status registers and FSMs. The final module here is called the reg map, which is basically just a register map, and it serves as the hardware-software interface between the software which is running on the CPU and the hardware accelerator which is running on the hardware. So at the for each block, the software running on the CPU will use an API to get the results of the block validation from the hardware, and then just commit and add the block to the ledger on the CPU side, just like any other software-only validator peer. So let me go into a little bit of our details of our hardware-friendly protocol, but I won't be able to cover everything, but would just like to give you the high-level idea here. So since we wanted to be able to process the block and all of its transactions right in the hardware without any involvement of the CPU, what we did was we looked at the block structure and we figured out that it could be broken down into three different sections. One is the header, then there are a bunch of transactions, and there's some metadata. And then we take each of these sections and basically send this data in a separate packet. So for example, on this side, you can see the header goes in a separate packet than the transaction one, and so on until the metadata. But to make sure that we can actually fit in the data from these sections into a single packet, we looked at the data which is typically included in the transactions. And we figured out there was a lot of repetitive data which could actually be sent only once initially and then can actually be replaced with certain encoded IDs. And that makes us reduce the size of this whole data, which has to be sent into a very small size, and then we can send it easily in a single packet. The other key point to note here is that all of these packets are self-contained. So they have certain annotations inside their headers, and those annotations let the hardware directly know where the relevant data is, which is needed for validation purposes. So the hardware can then very efficiently extract the relevant data and then forward it to the block processor for further processing. So here is the overall architecture of the protocol processor. Again, due to time limitation, I won't go into the details, but this acts as the hardware-friendly receiver for our protocol. And here is a packet processor. Standard typical packet processor will process the incoming packet, uses the annotations embedded in its header to extract the data fields which are relevant for the block processor, and then transforms that data into the format which is required by the block processor and writes into some predefined FIFOs, like there's a FIFO for the block data, there's a FIFO for transaction data, endorsement data, and so on. So now coming to the block processor architecture itself, internally, it's a two-stage pipeline. The first stage verifies a block. So basically here, the signature of the orderer which created the block is verified. And then the second stage block validate internally validates all the transactions of this block. And it's a parallel pipeline architecture, as I mentioned earlier, and can process multiple transactions in parallel and in pipeline fashion. And once these transactions have been processed, the results are collected in order in a result FIFO, which is then forwarded to the RegMap module. If we look into the validate, block validate stage, the second stage, that internally consists of three-stage transaction level pipeline. So here, all the processing is being done at the transaction level. And if you look at the first and the second stage together, this gives us a parallel pipeline architecture where we have multiple ECDSA engines distributed into these two stages. And each stage here can have multiple instances of the verification logic, as well as can have multiple instances of the VSCC logic. The important point to note here is that all of this is configurable. So based on the application requirements, we can configure how many of these parallel validators we need here, or how many of these parallel ECDSA engines we would need for evaluating the endorsements of a particular transaction. And the last stage here implements the update into the state database and the version concurrency checks as well. So there is an embedded key value database here. This stage will use the read keys, which are passed in through this FIFO here, to read those from the database, apply the concurrency and version checks on top of it. And if the transaction is found to be valid, then it will use the write set FIFO here to get its write keys, which are then finally updated into the database. And then all the results of which transactions are actually valid and invalid is then passed on to the next module, which is the register map module. So putting it all together, all these different components and modules I just described, we use the Xilinx OpenEC project, which is open source now. It's a lightweight shell which provides network connectivity with the CPU using QDMA subsystem and to the network interface using CMAC subsystem. And inside the user logic block, a user can actually implement their accelerators or whatever logic they want to implement or experiment with. So we basically implemented the protocol processor, the block processor, and the RegMap inside the user logic here. The protocol processor is connected to the CMAC subsystem, and the RegMap is connected to the QDMA subsystem. And if you look at it from the Fabric software peer point of view, this is how the whole hardware software partitioning happens. On the left-hand side, this is the typical software-only implementation. Everything runs in CPUs, but with the blockchain machine, all the bottleneck operations for verification and validation are run in the FPGA. And then we have provided a Go language API, which with the Fabric software peer running on CPU can use to read from the hardware registers and then commit the block like the block would be committed here with a CPU or software-only implementation. Going into the evaluation of our accelerator, here is a quick overview of how we set up a Fabric network. So we have two organizations. You could assume this is Bank A and Bank B. There are three peers here. One of them is a blockchain machine hardware accelerator peer, and this one is a software-only validator peer. So we would be looking at a comparison between this peer one here with peer two here. And these are the standard setup which are typically used for evaluation of Fabric networks, using a tool called Caliper, which can create transactions and send those transactions to the peers in the network. Here is a summary of some results, the highlights of the results. We looked at block latency, which is the total time spent in the validation phase, validating the block, and then how many transactions were committed per second. And when computing these two metrics, we did not include the time for writing the block into the ledger, because in both cases, whether it's blockchain machine accelerated or software only, the ledger write operation always runs on the CPU. And if you look at these blue line here versus the orange line is for the blockchain machine, and the blue line here is for the software only implementation of Fabric. And we were able to see a 10x speed up in most of the cases across different block sizes. Likewise, if we change the number of CPUs for the software-only implementation, or we change the number of parallel validators in our blockchain machine accelerator, we were able to see a much better speed up, because the hardware is using those verification engines much more efficiently than the software implementation using CPU-only verification. In terms of the resources, we looked at a few different configurations. 4x2 here means we use 4 different parallel validators, each having 2 ECDSA engines. And if we scale it up to 16 parallel validators, we were still able to use about 50 to 60% of the resources of the Alveo board. This suggests that we can actually have the rest of the resources either for more parallel validators, or we can use those resources to improve and optimize the ECDSA engines better, and then have a much lower latency for each verification itself as well. So to conclude my talk, this work basically shows that permissioned blockchains can really benefit from network-attached accelerator and FPGA programmability, because enterprise applications built on top of permissioned blockchains need customization. And the initial results from our proof of concept are quite promising. So right now, we are focusing on open source contributions. Hyperledger has a scheme called Hyperledger Labs, where you can launch upcoming projects so that the community can use them and experiment with them. So we have already launched that project, and we are going to be updated quite regularly in the coming weeks. So stay tuned, and the link is embedded here. You might also be wondering how this is all related to XACC, although we did not use XACC per se for this project, but our setup is very similar to XACC setup. So now we have just started looking into the NUS XACC setup, and we are planning to port it and set it up in XACC. So people who want to experiment with this without going through all the effort of setting this up would actually benefit from that setup. So here, I think, yes, I'm almost out of time. So yeah, I'll stop here. And if you have any questions in the chat, I will definitely answer them by just replying to you. Thank you for listening.
Thank you very much, Haris, for a great talk. So I think you've just about preempted the first question in your last point, but maybe I'll put it to you anyway, and you could give an overview of what's required to set this up. So the question was specifically about the Hyperledger Fabric package and how that would be set up on the machines. As I say, maybe you could give just a brief overview of what's required, and maybe we could put anyone who is interested in this in contact contact with you after the talk?
So generally for the blockchain machine, we just take the standard open source Hyperledger Fabric, and then we have made some changes to some parts of that code, which basically requires how we get the data using our protocol, and then how we get the data from the hardware. And we have provided a package/API for that. So that has been open sourced, and we will be updating it as well in future. So you should just be able to take that and then compile it just like any other Hyperledger Fabric code, and then should be able to get the peer binaries which you can then run.
Okay, thanks very much. So we'll move to our second speaker for today. Our second speaker is Xinyu Chen, a doctoral student in NUS, and he will present on ThunderGP. This is graph processing using high-level synthesis on FPGAs.
Right, so can you see my screen?
Yep, perfect.
Okay, good. So let me start. So I'm very happy to share my work at this event. So today I will talk about HLS-based graph processing on FPGAs. Let me start give you some background about graphs. So nowadays, large graphs are everywhere because the graph structure can represent the datasets from many important application domains, such as social networks, web graphs, and biological networks. More importantly, these graph data are getting larger and larger. For example, Facebook graph has more than 1 trillion edges, and the World Wide Web graph has more than 200 billion edges. And the largest graph, which can be the human brain, it has up to 1 quadrillion edges. So with such large-scale graphs to make the graph analytics useful and practical, we do need high-performance graph processing, right? That can respond to the graph queries as soon as possible. To achieve high-performance graph processing, the first problem we need to figure out should be what kind of architecture should we use for graph processing. Yeah, I know this is XACC talk. This work should be done by FPGA, but I need to make the story complete, right? Okay, so the first architecture comes into mind should be CPUs, because CPUs are very general and they have advanced compiler and memory hierarchy, and they are in every server. However, CPUs suffer from a very challenging problem, which is the end of Moore's law and the dynamic scaling. In this figure, we show the original Moore's law and the real Intel microprocessor transistor density. As you can see from this figure, the gap between them is getting larger and larger, which indicates the end of Moore's law. In the second figure, we show the technology according to the time and also the power consumption per silicon area. As you can see from this figure, with more advanced technology, the power consumption is not constant anymore. Actually, it's increased a lot here. So with these two facts, the successive CPU generations are unlikely to sustain the performance improvements required by big data applications. Once there are challenges, there are solutions, right? Just as advised by Hannes and David Patterson, we are in a new golden age for computer architecture. Domain-specific architectures, such as which is DSAs, can be promising solutions in the future. This is because DSAs are more closely tailored to the needs of the application. So GPUs, FPGAs, ASICs are three commonly adopted DSAs, right? So which DSA should we pick for graph processing? Here we actually pick FPGAs with the following considerations. Firstly, for GPUs, although it has very powerful computational capacity and also is very flexible, but it suffers from branch divergency. This is because graph processing is typically irregular, but GPUs are more suitable for batch processing. Another well-known issue is that GPUs are power hungry. On the other hand, for ASICs, definitely it delivers the best performance and the best energy efficiency. However, the drawback is also very significant. It has poor flexibility, and also it takes a lot of time from design to tip out. Maybe after you tip out, your algorithm has been changed, so you can never catch up the market. Instead, FPGAs are in another level of trade-offs. You can also customize application logic with FPGAs, just like ASICs. So you can give fine-grained parallelism to omit the branch divergency. And also it has reconfigurability. So it can adopt it to evolving applications such as graph processing algorithms. Lastly, it's noteworthy the FPGA's programmability has been largely improved with the recent trend of HLS. The basic idea of HLS is, I think everyone knows it here. We can program FPGAs with C or C++ rather than the low-level hardware description languages. Besides, FPGA-based accelerators have demonstrated promising results for the diverse data center applications. We submit this from existing studies. So we target FPGA-based graph processing, especially with HLS developing method. So here shows our journey of graph processing FPGAs. Today I will mainly talk about two works here. The first one, we figure out what are the challenges of graph processing accelerators with HLS. And then we seek the problem from another level to see whether there are system-level support for graph processing on FPGAs. Unfortunately, through the study of existing works, we didn't find such systematic work. So we proposed the first and open source HLS-based graph processing framework on FPGAs. Okay, I will first talk about the challenges in designing the accelerator with HLS. I need to first introduce the main computation of graph processing, which is the edge traversal. Let's say the push-based edge traversal. The idea is that the source vertexes pushes their properties to their neighbors. Let's say this vertex 1 will pushes its vertex property to vertex 2 and vertex 7. So in terms of execution hardware, we have a vertex property array. Right, so for operation, we firstly read the property of vertex 1, and we do some self-calculation, and then we accumulate it to the vertex 2's property. We do the same thing for vertex 7. So through this computation pattern, we can find some features of graph processing. The first one is that they have massive random memory accesses because the neighbors of a vertex can be far away from each other, and also it's data dependent. So it's not predictable. So the access to vertex property array will introduce a lot of random memory accesses. Secondly, they have high communication to computation ratio because we read several integers here, but we only do one accumulation, right? So to achieve high throughput for this computation, there are 7 common techniques for graph accelerators. The first one is vertex buffering with VRAMs, such that we can avoid the random memory accesses to the vertex property array. The second one is multiple processing elements, because we want to process multiple edges per cycle to increase the throughput, right? So combine them together, each PE can process a partial or buffered data. Okay, so since every PE processes different data, we need a logic to dispatch these edges to corresponding PEs, right? So in this case, for vertex 1, it has 2 edges here. That the first edge should be dispatched to P0 because the P0 buffers vertex 2's property, and the second edge should be dispatched to the P1 because the P1 buffers vertex 7's property here. So we need a this shuffling logic here. Although this figure shows static connection of the circuit, it's just an illustration of this example graph. In reality, the vertexes can be arbitrary. So we need a logic here to select the corresponding PEs, that is data shuffling. Let's first define the data shuffling. Basically, it's widely used for many irregular applications. The basic idea is that we have data tuples generated from the upper stage. Then we want to dispatch these tuples to the PEs, and which PE to go is determined by the value of the tuple. So this connection cannot be determined at compile time. We need to determine which PE to go at at runtime, right? So we need an all-to-all connection here. So actually it has runtime data dependency here. It's very challenging for HLS. This is because firstly, fine-grained control logic is generally not supported by HLS, right? So the network-on-chip solution, which is a typical HDL-based solution, is not available generally. Secondly, there is no vendor-specific extension for data shuffling, which has been argued by another work here. Lastly, HLS only conducts static analysis at compile time, so it cannot automatically extract the parallelism in functions with runtime data dependency, such as this case. We then also, search some related work to see whether there are some potential solutions to solve this problem. The first potential solution is the pooling method. The basic idea is that each PE checks these data tuples serially to see whether they need to process. However, the drawback is very significant. We introduce bubbles because we waste some cycles in checking the tuples that don't need to be processed. So with this solution, we actually need 8 cycles to dispatch a set of 8 tuples. So the parallelism can be only 1 tuple per cycle, right? Another solution is convergence kernel. The basic idea is that each PE writes the wanted tuples, which is the tuples to be processed by current PE, to a local VRAM in parallel. Actually, it's a local buffer. However, the problem is that the right index of wanted tuples are dependent, right? The right index of a tuple is determined by whether other tuples need to be processed. So the runtime data dependency is still there and it's not solved. Our compiler tells us this method has very high RI that can be up to 300 cycles, which means we need 300 cycles to dispatch a set of 8 tuples here. So we are thinking these two potential solutions do not solve the problem. Pooling method introduces bubbles and convergence kernel doesn't solve the problem, actually. So we're thinking, what if we know the positions and the number of wanted tuples for PE in advance, such that each PE can directly access the wanted tuples. So we don't need to waste cycles in checking the unwanted tuples, right? So the problem comes, how can we know the positions and the number of wanted tuples? So actually we propose a decoder-based solution. Because for a PE, a tuple only has 2 statuses, to process or not to process. So for a set of 8 tuples, then we only have 256 possibilities. So we can enumerate them and we can look up them at runtime, right? Here I will use an example for a set of 8 tuples on PE0 for illustration of our method. So firstly, we have 8 tuples here and with their indexes here. The first step, we calculate these destination PEs of these tuples in parallel. Let's say the index 6 and index 2 will go to the destination PE0 here. We then compare their destination PE ID to current PE ID, which is 0 here. So if they are matched, we set the mask bit to 1, otherwise we set it to 0. So as you can see here, the index 6 and index 2 will be set to 1, right? So with this mask code, we can decode out the number of tuples to process and also their positions. The basic idea of decoder is a multiplexer right here. So with this decoded information, we can directly collect the wanted tuples serially. So we can set the trip counter to a number of wanted tuples, and in each iteration, we can fetch the tuple according to the positions. So the proposed method actually does not introduce bubbles. We do not waste any cycles, and the runtime dependency is resolved. We do not leave the dependency to the compiler, and all these modules are pipelined with HLS or FPGAs. So we evaluate the efficiency of shuffle. As you can see from this figure, the measured throughput is very close to theoretical throughput, which indicate our method can dispatch n tuples per cycle. provide sufficient parallelism. We also compare with existing method potential solutions. Our method is much faster than existing methods. We then we think that is the challenge of graph accelerators with HLS, and we have solved that problem. So then we are looking at the problem at a higher perspective. We are thinking on the high level, we have graph applications for different use cases from developers. And on the back end, we have CPU FPGA platform that providing the computation for these graph applications. So we are thinking, what should we have in between? Should we just have graph accelerator design methods? We don't think that's enough, because really only with these methods, the developers, they all need to design from scratch, do optimizations from scratch, and debugging day by day, right? So what we actually need is system level support to bridge the high level graph applications to low level CPU FPGA platforms, such that the developers can spend very less efforts in designing, and then can enjoy the FPGA accelerated graph processing. So we first survey the existing FPGA-based graph processing works to see how systematic are they. Can they handle this task? And we basically survey the FPGA-based graph framework and library, and also the accelerator architecture from the following perspectives. Firstly, from APIs and programming languages, most of them do not have APIs, and they are designed with hardware description language. And most of them do not have automation that tunes the accelerator with the input, with considering the input from developers. In terms of evaluation, most of them are conducted with simulation, which can be far away from the real implementation. So I think many people can understand this point. And they only value a few applications here, and most of them are not publicly available. So in summary, we think they have pretty poor programmability due to the HDL-based programming and no user-friendly APIs. And they require manual performance tuning, such as pipeline composing and design space exploration. Lastly, they have poor usability because they are not open source and there are no ready-to-run systems. So considering all about this, we think we need a high performance and easy to use graph processing system for FPGAs. So we determined to design one. Of course, to achieve high performance and ease to use is not easy. There are several challenges. Firstly, we need to support various graph processing algorithms because there are so many algorithms such as BFS, SSP, PageRank, WCC, and so on and so forth. So to tackle this problem, we actually design an efficient architectural template with the adoption of the guess model. Basically, it's a trade-off between specialization and performance. Secondly, we need to enable programming without hardware expertise because most of the graph application developers are from data science domains. They are not supposed to know about hardware details, right? So to solve this, we actually expose only high-level APIs to developers, and our system will take the rest to generate the accelerator code. Lastly, the state-of-the-art FPGAs are pretty complex. They include multiple SRs and multiple memory channels. It's very important to unleash these potentials, right? Because performance is always of the first priority. So to solve this, we explore heuristics to scale our accelerator template to multiple SR FPGAs, and also we schedule the graph data correspondingly to make the accelerator busy. All these techniques are integrated into ThunderGP, which is an HLS-based graph processing framework on FPGAs. Here shows the overview of ThunderGP. Basically, it has accelerator template, which provides a general architecture for different graph processing algorithms. And also it has accelerator generation, which produces synthesizable accelerator code with the input of developers and the accelerator template. On the host side, ThunderGP has graph partitioning and scheduling algorithms to schedule to coordinate the graph data with the generated accelerator. In terms of using the ThunderGP, the developers just need to assign the functions of the scatter together and the pi to customize the logic of the graph accelerator. I will introduce their functions later. Then the developers need to assign the hardware platform to the system, because our accelerator generation considers the specs of the platform to fully utilize the platform. Yeah, right. So the accelerator can be generated automatically. We can fit them into Xilinx development environment for the bit strip of the accelerator. Then on the host side, the developer just need to assign the graph dataset. The graph partitioning and scheduling can be automatically, evoked to coordinate with the accelerator. Finally, the application can run in a push-button manner. In the next, I will introduce the accelerator template and the accelerator generation, which scales the template to multiple SLRs. And finally, I will introduce the graph partitioning method and also the scheduling method. So here is the accelerator template. Basically, it adopts the guess model for generality. It's widely adopted for many graph frameworks, actually. It contains 3 stages. In the first stage, which is scatter, basically for an edge, it generated update tuple. So here, for this example, the vertex 1 will generate 2 tuples here for vertex 2 and vertex 7, respectively. In the second stage, which is gather, we accumulate the values to corresponding destination vertices. So here we will accumulate the x with vertex 30 over to vertex 2 and y to vertex 7. Finally, we have an apply stage that updates all the vertices for the next iteration. So ThunderGP exposes 3 APIs of the accelerator side, such that the developers can customize the accelerator for their own needs. So in terms of optimization of the template, we firstly adopt destination vertex buffering with RAMs to avoid the random memory accesses, and we also adopt multiple PEs with shuffle that can avoid data reordering, and also we can enlarge the graph size processed on chip. Yeah, just as the technique I presented in the last work. Finally, we pipeline the scatter and the gather inside FPGA, such that we can reduce the memory accesses to the global memory, and also we can better exploit the pipeline parallelism. However, the side effect is that ThunderGP accesses source vertices from the global memory directly. Although source vertices are in ascending order with standard graph formats, each access still issues one request to memory, as there is no transparent caches in FPGAs, right? So we need to conduct our own memory optimization. So we analyze this access pattern and have 4 memory optimizations here. Firstly, we find these data blocks have very good data locality. Many accesses they have very high data reuse, so we deploy caching here. Secondly, we deploy coalescing, because the requests to different source vertices from different scatter PEs are not too far away from each other, such that we can coalesce them to reduce the number of requests to the global memory. Thirdly, because the request addresses are monotonically increased, so we try to prefetch these source vertices for future use. Lastly, graph is irregular, and the throughput is usually frustrated. So we deploy the execute access decoupling to such that sometimes the access can be happen ahead of execution. Then we scale our architectural template to multiple SRs. Our principles are that we never let kernels cross SLRs for better timing, and we fully utilize the memory bandwidth of the platform because these applications are essentially memory bounded. Following these principles, we have two automated steps. Firstly, we calculate the required number of kernels to satisfy the memory bandwidth of the platform, and we fit these kernels to multiple SLRs. So the main idea of calculating this number of kernels is that we know how many tuples, how many edges we can process per PE, and we know how many tuples we can read from the per cycle from the memory interface, so we can balance them by tuning the number of kernels, right? Then we can scale the number of kernels to the number of memory channels to fully utilize all the memory channels. Then we try to fit these kernels to multiple SLRs. We model it as a multiple knapsack problem because different PEs have different resource utilization and different SLRs have different resource capacity. As you can see from this figure, some regions are occupied by some built-in functionalities, right? So after fit them into SLRs, we finally interface them with the closest memory interface. So far, we have the synthesizable code for the accelerator. Then we need to schedule the graph data to coordinate with the accelerator. ThunderGP adopts a very simple destination vertex cut graph partitioning method. Let's say this example graph with the original graph layout in COO format. The basic idea is that let's say one FPGA can buffer 3 vertices here, then we simply partition them into 2 partitions. The edges with the destination vertices from 0 to 2 will go to the partition 1, others will go to partition 2. So as you can see, there are no edge reordering or sorting operations, and the complexity is just OE, right? We then try to schedule these partitions to multiple kernels in the accelerator. We first divide a partition into chunks with edges equally partitioned. This is because for some small graphs, they usually only have one partition, but we have multiple compute units in hardware, right? So to fully utilize them, we partition these edges for them. Then if a graph has many partitions, then we estimate the execution time of these chunks by a regression model. So then we deploy a greedy search solution to find the global scheduling plan. So we can find an optimal scheduling plan with different partitions. The main idea is to keep every computer units busy, right? Finally, we schedule these partitions into real hardware computer units. In terms of evaluation, we conduct on 2 hardware platforms with different SLRs. And we use 7 applications for evaluation, and we use 14 graph datasets for evaluation also. Here we first evaluate the efficacy of memory optimizations. As you can see from this figure, all the optimizations contribute to performance, and the speed up can be up to 32 times compared to the baseline that doesn't have any optimizations. And then we evaluate the scalability with varying the number of SLRs and number of memory channels. As you can see from this figure, our speed up is very close to theoretical speed up, which is 4 here, because we have 4 memory channels here. Finally, we compare with state-of-the-art works. Compared with RTL works, we have up to 2.9 absolute speed up. It's noteworthy that this work is based on simulation, even though we still have speed up because of the novel design of the microarchitecture. And compared to HLS-based library, we have up to 30 absolute speed up. Yeah, and also ThunderGP is publicly available and also is featured in Xilinx apps and libraries. You can get started with it on GitHub. Okay, that's pretty much about my presentation. For summary, we first talk about the challenge of graph accelerators with HLS. Then we propose ThunderGP, which provides a system-level support for graph processing on FPGAs. That work aims to make FPGAs for graph processing possible and popular. I want to thank my collaborators and also want to thank Xilinx for their generous hardware donation. Okay, that's all about my presentation. Thanks for listening.
Let me go to the first question that I saw. So this was a multi-part question from Amin. He was also reviewing the paper to go with the ThunderGP talk. I'll try to parse the questions for you, so I'll do my best here. In slide 1, you showed examples of huge graphs. Why are the data sets in the paper small, except one? And are the small sizes beneficial for the accelerators that you are using?
Evaluation, we use 14 graphs, and for some of them are pretty large. I think let me look at them. Like Twitter and graph 500, they are pretty large. They have up to 200 million edges. But now we are, because FPGA also have constrained, memory capacity. I mean the device memory. Now the graphs processed on FPGA cannot exceed that capacity. Yeah, so for processing very large graphs, definitely there are some new challenges we need to do step by step. And finally, essentially, maybe we need to look at distributed graph processing because, if the graph is very huge, one server cannot store them. Yeah, that is ongoing work of ThunderGP.
Okay, thank you. And I think you've already addressed the second part of the question, or to some part, but let's just go ahead with it anyway and see if you'd like to add anything else. The second part of the question, why did you not compare with CPU or even GPU distributed libraries like Galios, Gemini, and others? If graph processing is memory bound, what is the advantage of FPGAs versus CPUs? The contention CPUs have large, cost-effective memories, and conventional CPU programming is easier.
All right, this is a very good question, and it's a very challenging question, right? So I think the best thing is that with FPGAs, we can customize the hardware logic for graph accelerators, and also the more recent FPGAs have HBMs, right? In some cases, we can gain energy efficiency or this kind of stuff. Compared to GPUs, currently we cannot say we outperform them because there are too much difference in terms of memory bandwidth, right? GPUs has up to 900 gigabytes bandwidth per second. So which is much higher than FPGA current DDR-based boards, which is only maybe 70 gigabytes per second. That is a very good question. I mean, but if we are looking at distributed graph processing, we may have another advantages, such as we can have direct IO connect for FPGA boards. All these are opportunities we need to work on. It's a very challenging question.
Absolutely. It sounds like a good question or a good topic for further discussion. Again, this was one of the intentions of the XACC program to encourage these types of discussions and opportunities for collaboration. So a little plug for the program. How did you achieve the implementation, so the decode of the positions and the number of tuples that you desired or that you required?
The idea is that, we can enumerate the positions and number of wanted tuples for all the possibilities, right? So we can, store them in a multiplexer or in a table. Then we can look up them at runtime. Because, for a set of 8 tuples, we only have 256 possibilities. Then we can just store all these cases with their positions and number of wanted tuples information into a table. Then we can look up this table at the runtime. And also we can use some compressed data format for their positions. For example, we can use my integer to represent all their positions we need to process.
The last two questions I see, ThunderGP is already installed at the NUS XACC. Is it ready to be deployed at other XACCs, or perhaps you could comment on its current status? I know you showed some information at the end of your talk, but perhaps you could elaborate a little bit more.
Yeah, actually, it's released on GitHub. You can deploy on any server. Actually, yeah, now it's on XACC. You can run it by by simple, make, by a simple make, right? It's just open source. You can run it in a push button manner. Yeah.
Great, that sounds great. Thanks. And the last question is, do these graph applications benefit from FPGAs with HBM high bandwidth memory, like the Alveo U280 that's available in the XACCs?
Yes, definitely. We are working on this. We are working on extension of ThunderGP to benefit from this HBM, but there are several constraints there we still need to work on. For example, the first one is that we have massive memory bandwidth, so we now cannot guarantee the enough number of kernels to consume this memory bandwidth. So the system bottleneck shifts from memory to resources. So we need to consider to redesign the hardware accelerator. And also, HBM has limited capacity, right? Only 8 gigabytes in the U280, right? So there are several challenges there. We are trying to tackle that. But the main idea is that we need to make the kernels, resource efficient, so we can try to consume all the memory bandwidth of the platform.
Okay, and maybe one more question about distributed implementations. Is this something you're actively working on? And our last XACC Tech Talk, we had speakers talking about network implementations with Vitis for the Alveo hardware. And we also heard an example of machine learning elastic DF, so a distributed machine learning example or application on the Alveo hardware.
Yeah, this is a very good question, and it's also very good suggestion. We are actively working on this problem. Actually, it's not just the distributed problem, right? We actually want to work on the scalability issue of graphs, because once your graph is very large, then you need to have multiple board, maybe multiple board in one machines and multiple boards in different machines. Even with HBM, we need to have multiple PEs. The PEs number should be much more than DDR-based board. So scalability can be a very challenging problem for graph because graph structure is very irregular and you cannot easily partition them. So we are basically working on this problem. It can include HBM-based solution and also distributed-based FPGA solution. So, and for network connection, definitely we will consider the open source network stack from ETH. It's very, we can, reduce a lot of development efforts, right? We can join their efforts somehow. Yeah.
Okay, thank you very much. That covers all the questions. So I'd like to thank everybody who attended, and thanks again to both our speakers. And with that, I'll close the session.